Oh, okay. Oh, got the recording working. Okay. Well, okay. Give me a second. I'm gonna pause the recording. I'm gonna check my audio really fast. Okay. Sorry, I just needed to check up on that, make sure everything was working all right. Good evening, folks. I am sorry about last night. I hope you guys are ready to talk about Chapter 8, where we're beginning in Section 8.1, and then later on to talk about Section 8.2. So we're talking about conditional probability and independent events today. Both of these are fairly important concepts that you need to be able to understand. Again, when I was reading through this chapter and doing a lot of the problems, the biggest thing I struggled with was the lingo and the way that they wrote things down. So that's probably what I'm going to focus on today. I didn't receive any questions on through email or on Canvas. So just a reminder, you guys can feel free to do that anytime, and I'll talk about whatever you want me to talk about, whether you're here at the GSG or not. So to start with, let's talk about conditional probability. Okay, and like I said, both of these concepts, the independent events and the conditionals stuff, are very important. I'm just going to write down the equation that is found on page 423, which is this. Okay. I don't know if you guys want to talk about this kind of stuff, but I'm just going to briefly explain what this equation kind of means and why it works. And you feel free, of course, to skip over this section if you're completely comfortable using this equation, but it took me a little while to get used to it. Okay, so this, of course, is the probability of event E happening. Given F happens. So not only does E have to happen, F has to happen. How do we think about this? We thought about this in terms of tree diagrams. When we have, I believe there's a problem like 15 or something in the, I lied, it's not problem 15. Anyway, so you can, for instance, I don't remember what problem it was, but it matters, for instance, if this is A, B, C, D. I think this is one that we're going to be doing a little bit later on. It matters if you get to C via point A or via point B, because going A to C is not equal going B to C. So we care about the means of getting there. We care about other things that are happening other than just the specific event that we're thinking about. So the probability of E that is happening given that F also happens. So in terms of thinking about this, this equation actually makes a lot of sense, because this is the probability that E intersects F, or what E and F have in common. That is not entirely legible, and I apologize for that. So this top term refers to what E and F have in common. And then this bottom term here refers to the prob that F happens. And so both of these make sense. If E and F had nothing in common, if the probability of E intersecting F is equal to 0, then the probability of E and F both happening also has to equal 0. Because E and F can't both happen if they don't intersect at all. So we're looking for the times that E and F intersect, but also we need to make sure that we need to include the chances that F does happen. Because if there are very low chances of F happening, then it's tougher to, obviously, like there's less of a chance of hitting one of those intersection points. So that's what this equation kind of means, the different pieces of it. This is very useful in terms of solving problems. In addition, they talked about a theorem on page 425 called the product rule, which is basically just shuffling the stuff around. It's the probability of E intersecting F being equal to the probability of F times the probability of E given F. And so this is basically just the algebraic shifting around of the equation, or of the pieces of that equation. And yeah. So that's what's going on with this equation. And it's just important that you understand, number one, the lingo, that's E given F happens, and it's important that you understand why this equation works, because we're concerned about when E is intersecting with F and how possible is it that F actually happens. So that's why we have all of these probabilities combined to make this equation. Okay. Okay. Okay, let us begin on page 429. So this is section 8.1. And we are going to start with the skill building, the beginning part, problem 5, problem 7, problem 9, problem 11. Okay. So let's first look at number 5. Oh, it looks like I have another person here with me. Welcome. Thank you for joining. Okay. So we're going to start by looking at the probability of E happening. And if you don't have your books with you, basically what this looks like is there is a Venn diagram where one of them is the probability of E and one of them is the probability of F, and they're both in the same sample space, and the numbers inside look like this. Okay, so the probability of E, we're only looking at the chances that E is happening. So not only do I have to look at the chance that E happens on its own, but I also have to look at what happens if E and F both occur. I don't really care if F is also occurring or if they're intersecting or anything like that. I just want to know what the chance is that E happens. And so the chance for E happening, the probability of E is going to be equal to 0.2 plus 0.3 or 0.5, because it's both of these numbers, not just this one here. Okay, so then let's take a look at problem 7. Now we're looking for the probability of E given that F also happens. Okay, what does that mean we're looking at? Well, we need to find the probability of E intersecting with F, and we need to find the probability of F if we're going to use the equation that we used for like the equation that we just like generated, so, or got from the book, excuse me. So we have E intersecting with F and the probability of F. So the probability that E intersects F is going to be this here. This 0.3. The probability that F itself just happens is not just going to be 0.3, but 0.3 and 0.4. So this is 0.3 plus 0.4. Because we don't care when we're looking at just the probability of F, just like when we were up here caring about just the probability of E, if E is happening at all. We just need to know what the probability is if we stick 10 numbers in a hat, we pull one number we associate with F. Okay. So the way this is going to work is that we're going to have probability of E given F is equal to 0.3 over 0.7, which is this chunk here, which we can simplify down to just 3 over 7. And I believe, hang on, let me pull a calculator out. Okay. So this is 0.28 or 0.428. So that is the probability of E given F. So it's not just the intersection here, because as we were describing earlier, the intersection only describes like intersecting points of E and F. We also have to take into consideration that F may not happen. And if that is the case, like how does it impact the chances of E given F? Okay, so let's try number 9. And just a reminder, I urge you guys to just like take a sec to pause the video just to think about the problems, maybe do them on your own, because it can be really helpful to just try to like power through, and then also like have me to like talk about the answers with you guys. Okay, so this is the probability of E intersecting with F, which we just established up there. This is the intersection point, the 0.3. So that's what we have. What about this last one? This is the probability of E, this bar over top. And if you remember, this bar refers to not. So basically, we want to know the probability of not getting E. And the easiest way to do this, if you remember, is say, okay, so I know the, ooh, that's a really ugly shade of green. I didn't mean to pick that. Okay. So I know the probability of getting E, and I know the probability of getting anything that's not E is the total probability of something happening, or 1, minus the probability of E. So the way that I solve this problem is just by saying 1 minus 0.5 is equal to 0.5. So this is equal to P not E. So the chances of getting E are 1/2, and the chances of not getting E are 1/2, and that makes perfect sense because if you add them together, it's 1, which is the chances that either you get E or you don't get E. And that makes sense because there's really no third option. Okay, so that was problems 5, 7, 9, and 11 in section 8.1. If you have any questions, of course, feel free to email me. Okay. So let's also do, this is the same page. Sorry, I just erased like everything that's on there. Maybe it's not the same page. Let's try problems 21, 23, and 25. So this is actually page 430. Okay. And so here we're looking at a tree diagram, and we're trying to analyze what the tree diagram is telling us. This is kind of, I like briefly talked about this earlier. We have this branching into A and B, and then both A and B branch into C and D. And all of these have different probabilities. And you'll notice that 0.7 and 0.3, both at, when you add them, you get 1, which is the probability that either A or B occurs, because again, there's no third option. And the same goes for each of these. Okay, so for problem 21, what we're looking for is the probability that C occurs. Well, I can see 2 points on this end that give us C. There is a 0.7 chance we get A, and then from there there's a 0.9 chance we get C. So this is the process of going from A to C. And then there's also this process down here where we go 0.3 chance of getting B and then 0.2 chance of getting C. So this is B to C. So if we add all of these up, this is 0.63 plus 0.06 is equal to 0.69. And that is the probability of getting C. So it's much more likely that you're going to get C than D in this example. Okay, just want to clarify that's a 3 down there, that's an 8. 8. So it's 2 and 8. Okay. All right, so then what is the probability that we get C given that we also get A? So basically what we do is we know that if we go and we take this route, we end up going through B, and we have to go through A. So given that A occurs, the chances that C occurs is going to be in terms of like what we wrote down. We have this whole equation. Do you think we should use this equation right here? Probability of C intersecting with A over the probability of A dot, 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 dot. Well, basically, I don't think there's really a need to, because the way that this is set up works so nicely for us. The probability of C given A is this number right here. It's just going to be 0.9 because we already are at A. We don't, like, we're assuming that that A has occurred. So what is the probability of C occurring given that A has occurred? And so we know that from a tree diagram is 0.9. Okay, so finally, let's do problem 25. And this is the probability of C given B. And so this is the same process. We can't go through A, we have to go through B. So given that B has already occurred, what is the chances that C occurs? So one way maybe to think about this problem is that let's say you're walking down this path, and there are a variety of different branches you can take. So you walk down this path. What are the chances that you walk up C? You're here when you make that decision. You cannot, there's no chance you're going to go down path A because you've already passed that juncture. So given that B is a certainty, what is the chances you get to C? And that answer is 0.2. Okay. If there are any questions, again, feel free to email me. Okay. So let's take a look at some of these applications.
Olivia?
Sorry. Give me just a sec.
Okay.
Okay, so let's take a look at some of these applications. Let's start with problem 33. One sec, let me reorient my stuff here. Again, I would encourage you to just take a moment, go ahead and do this problem on your own. This problem goes, for a 3-child family, find the probability of exactly 2 girls given that the first child is a girl. Okay, so we know one way to think about this is through a tree diagram that we just built, just like the one that we just worked with. We have a girl, we have a boy, girl, boy, girl, boy, and these are for 3 children, so girl, boy, girl, boy, girl, boy, girl, boy. Okay, so where are we in terms of this tree diagram right now? Well, it's given to us that the first child is a girl, so we're right here, and we need 2 girls. So if we take this path, we get 3 girls. So that's not something we want. And if we take this path, we get 1 girl, which is also not something we want. So we need to go girl, boy, or boy, girl. Basically, what this means is we have, assuming, of course, that it's 1/2 chance getting a boy or girl, it's just a flip of a coin, it's going to end up being 2 out of 4 options, or 1/2 chance of getting 2 girls, given that child number 1 is a girl. I think this question, honestly, in my opinion, when I first read it, there was a little bit of ambiguity, do they want 2 more girls? But really what they're asking for is we need 1 boy and 2 girls in this family. Okay. So for a 3-child family, find the probability of exactly 1 girl given that the first child is a boy. So we're going to do the exact same thing. Here we are with our first child being a boy. So this is where we're starting. This is given to us. A lot of the time in a problem, if you're given, if you're trying to find the probability of 1 girl given boy, this information, for instance, they are giving to you so that you can consider it the case. Okay, so if we follow this path, girl, girl, this is boy, girl, girl. That's 2 girls, not something we want. This path, oh, I was going to do that in a different color. This path is boy, girl, boy, that is something we want. Here we go, boy, boy, girl. There's also one girl there. And finally, we have boy, 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 3 boys. Not something we want. Okay, so what are the chances we get one of these check marks, these families with the 2 boys and 1 girl? It's, again, 2 out of 4, or 1/2. Getting 1 girl given child 1 is a boy. Okay. All right. So that's another example of using a tree diagram to I don't know, think about these kind of problems. So give me just a sec. I'm trying to find which problem to do next. Okay. Actually, I think since we're getting about halfway through the GSG, we should move on to 8.2. Oh, wait. I did want to do problem 69. Okay. Okay. So we're going to quick do 69 and 71, and then we're going to move on to section 8.2. Oh, I have a message in the chat box. Yes, absolutely. If you need, I'm sorry I didn't see this message. You can for sure ask for help on questions. Just specify which question it is. I don't think I can help you with homework problems, but I can for sure help you with problems similar to homework problems. So whenever you feel comfortable, just go ahead and put it in the chat. Okay, so I'm going to start problem 69. So we're on page 431. Okay, so we have this blood type table that I think we've worked with before. We're asking for the probability a randomly selected person has a blood type that is type B, given that the person is Rh positive. So first of all, I'm going to write this in terms of the lingo of this chapter. Okay, so now I know I'm only looking at Rh positive people. How many Rh positive people are there? Well, one thing about percents is that you can assume, for instance, that if there were, I don't know, if there were 100 people, for instance, for O positive, if there were 100 people, 39 of them would be O positive, 31 of them would be A positive. You can go down the list. So what I'm going to do is I'm going to look for all of the positives. So the chances somebody is Rh positive is 39% plus 31% plus 9% and 3. So I'm just going to add all of these together really fast. If my calculator will work. Okay. So I believe that is a 2. So there's an 82% chance of being Rh positive. Okay, yeah, for sure. Let me finish problem 69 and 71, and then we can go back and do problem 35. Okay? Awesome. Okay, so 82% chance of being Rh positive. Another way of writing this is the probability of being Rh positive is equal to 0.82. If you are going to try to like go through the, I guess that's probably a useful thing to do. Well, so let's do it like that. This is equal to the probability that B intersects being Rh positive and the probability that one is Rh positive. So now we found the probability of being Rh positive. The probability of B intersecting Rh positive is people who are both type B and who are Rh positive. In that case, according to this table, it is the people who are B positive or 0.09. So this probability of B given that a person is Rh positive is going to be equal to 0.09 over 0.82. Let's pop that into a calculator. And I believe that is 0.109. So there's about a 10% chance that if you are Rh positive, you have type B blood. And that makes sense. Another way to think about this problem is that, okay, so there's like 82 people, out of them, 9 of them are type B. It's essentially this exact same equation. I initially thought about it in terms of like, okay, so if I have these percentages, if I just had 100 people, 82 of them would have Rh positive blood, 9 of them would be type B positive, so 9 divided by 82 is going to be, and then you would get your percentage. Okay. Let's quick do problem 71. And then we're going to get to the problem that Jess mentioned in the chat. Oh, I lost my screen share. That's what happened. Whoops. Come on. Give me a sec. Oh, awesome. Okay, it saved all my writing. Marvelous. Okay. Okay, so basically we're going to do the same process for this problem, which is a blood type that is Rh negative, given that the person is Rh positive. Sorry, I was reading 72. Blood type is Rh positive, given that the person is type O. So we're looking for the probability of being Rh positive, given that the type is O. What we need to find are the probabilities of being type O, so that's 39 plus 9, so that's 48%, or the probability of being type O is equal to 0.48. The probability of being type O positive is equal to 0.39. So this is going to be the probability, or this is going to be 0.39 over 0.48. Same process, divide it out, and we're going to get 0.81. So there's an 81% chance that if you're blood type O, you'll also be Rh positive, which means most people who are O positive, which makes sense given the data that we have. Okay. So we have had a question asking us to go back and talk briefly about 34/35. 34 Okay. What I would do with 34 is very clearly define what things are. For 34, I would say the probability of 2 plus children given that one child already exists. I would use whatever notation you feel comfortable with, but I would make sure you write down explicitly, like, this is what I'm looking for. I need to find the probability that having one child intersects with having 2 plus children, which is all. So this is going to equal 1. And I need to find the probability of having. The probability has more than 2 children if it is known that it has. So it's not 2 plus, it's 3 plus.
Right.
Because we don't want families with 2 children. We don't want that. We want more than 2 children. So we want 3 or more. Okay. Okay. So then we're going to look for the probability of having 3 or more children. This is not equal to 1. I screwed up there. Don't listen to me. Okay, so basically what this is asking is how many families, I can't spell, have 3 plus children out of all families with at least 1 child. Okay, so basically how you want to think about this segment is not that, okay, so all like families that have 3 or more children also have 1 child, which is how I initially looked at this, which is wrong. What you want to say is how many families that have 3 or more children are there out of all the families that have at least 1 child. So you need to look at you need to find the chance of having kids at all versus chance of 3 or more. Okay, so that's what you need to look at for this. Keep in mind that this is the same equation that we've been using. So that's what you need to compare for up here. What is that intersection? What does that look like? Just like we were doing with the blood types, because we're given percentages, we're given a lot of chances, and it might not, like, solving the problem might not look like the way that you traditionally have been thinking about it, like in the Venn diagram kind of terms. Okay, then we also need to find the chance of having 3 plus children. So that's how I would go about setting up problem 34. And I can't give you numbers because I believe this is a homework problem. But yeah. So we don't care. We don't care about families that have no children. We're only comparing the people who have 1 kid, 2 kids, to the people who have 3, 4, 5, etc., etc. Okay. Did that help in setting up problem 34?
Yes, I think I reversed it.
If it didn't, I can talk about it some more. In terms of 35, okay. 2 cards are drawn in order without replacement from a regular deck of 52 cards. What is the probability that the first card is a heart and the second card is red? So there's no replacement. The way that I would approach this problem is by saying, what is the probability of pulling a, this is kind of relates to what we're going to be talking about in section 8.2 with independent events. What is the chance that you pull a heart? So, oh, awesome. Awesome. Ask any more questions if you need any more questions. Okay. So what is the chance that the first card is a heart? That is going to be 13 out of 52 because there are 13 hearts in a deck of 52 cards, which is 1/4 of the deck. So this is part 1. And then we also need, the second card has to be red. Another way to think about this is the probability of heart, or excuse me, the probability of red given heart. Okay, so we have the probability of getting a heart. Now we need the probability of red intersecting with hearts. It's like Valentine's Day. Sorry, Valentine's Day was 2 days ago. Intersecting with getting a heart. Okay. So this is, sorry, I'm just trying to set up the problem in a way that is absolutely clear what I'm doing. Okay. So that is 0.25. This is a little bit harder to think about. Okay. So I'm trying to think of a good way to explain this. Okay. Give me 1 sec. Okay. So Jess drew a tree model, which is probably a very helpful thing to do. So let's do that. Your tree model started with, so we have these four suits. Okay. So after that, red, black, but none of these matter because we didn't draw a heart. So the probability of getting a heart is 1/4. The probability of getting a red card after that is 25/51 because there used to be 26 red cards in the deck and there used to be 52 cards in the deck, but since we drew a heart, and that counts as a card, there are now 25 out of 51 cards that remain red. Okay, so then this would be 26 out of 51 to get a black card. So it's slightly more likely you draw a black card than a red card. What do you do with these? Well, this we know. This is a really good idea. This is a really good way of explaining it. This we know is the probability of, I wouldn't use this equation at this point in time. That's just not what I would use. My method of solving it would literally just be there's a 1/4 chance you get a heart times a 25 out of 51 chance you get a red card, and that's equal to 25 out of 204, which is what the book says is the correct answer. So that's how I would come to the correct answer. That makes sense to me. I wouldn't deal with all of that right now. Okay, that being said, now we have to figure out the probability of getting heart after we do a red card. So let's do the same thing. Let's build ourselves a tree. We have red card, black. We don't care about what happens in black. Then we have 4 suits. We don't care about any of those. So this is a 26 out of 52 chance of getting a red card. And this is going to be a, well, you can't really solve it the same way because you don't know if the red card is going to be a heart or a diamond, because the red card could be either. We know that there are 51 cards left in the deck, but there could be 13 or there could be 12. Yeah. So we're going to need to think of a different method of solving this, because this is probably not going to work. Just give me a hot sec, and I'm going to check up on something really fast. Okay, so we can't use this tree method because we don't know what's going on. We are actually going to have to use the equation this time around. I need it up there. I do need it down here. So I'm trying to think about how to think about the, okay. So we know the probability of getting a red card is equal to 1/2, because you either draw a red card or a black card. In addition, we need to find the probability of hearts intersecting with red. So basically, the problem we ran into was that we didn't know if it was a heart or a diamond. So basically, we need to figure out what are the chances that the heart, that that if it's a red card, it's a heart. So the probability that if it's a red card, it is a heart. That's 1/2. But the answer to this is not 1/2 divided by 1/2. So both options occur, so add them both in. What are you referring to? Sorry, I'm struggling with this problem too. Just an FYI, the answer in the book is the exact same for this. So the answer we're going for is going to be 25 over 204. So Jess, what do you mean by both options occur, so add them both in?
Can you hear me? I need to
Okay. So I'm thinking about this the wrong way because this is not referring to one card. This is referring to two cards. So that is just not something I need. The answer there is not 1/2. Because this is the probability of getting a red card this is intersecting. So you have, sorry, give me a sec. I'm gonna write down what you wrote down in the chat box. So Jess just said 12 over 51 and 13 over 51 times 1 over. So that would be 25 over 51 times 1 over 2. Which would give us not quite what we need. Because that would be 25 over 102. I'm not sure if that's how, I don't think that that's how you can't just add them together like that. That makes me a little uncomfortable, like adding them together in that manner. But give me a sec. Let me. Oh, that's not quite it either. Okay. I'm sorry, your microphone isn't working. Okay, so page 2 or page 427. Okay. Let's try redoing the tree diagram. And let's do it a little bit differently this time. Let's do it like we were doing it on page 427, like you suggested, but we're going to separate it out a little bit because I'm kind of struggling conceptually with what this term is, this probability of hearts intersecting with red. So let's just draw another tree diagram. Instead of doing red, we're going to divvy this up and we're going to do okay. So this is spades and this is clubs. I drew them in black because I'm not drawing any more there. This is hearts and this is diamonds. So we know what we want to look at is this hearts and diamonds path. So I see what you were doing. Hey, that was a good move. Sorry I took a while to catch up to what your plan was, Jess, but I see exactly what you did. That was good. That was good thinking. Okay, so we break up into this again. So this is the heart, and this is all of the other things that we don't necessarily want. And then there's things we don't necessarily want, and then there's a heart. Because all we care about the second round is getting a heart, and all we care about this first round is getting a red card, aka a heart or a diamond. Okay, so the chance of this happening is 1 over 4. Chance of this happening is 1 over 4. The chance of this happening is 12 over 25. And the chance of this happening is 13 over 28. Why did 25? It's 51. 51. Lord have mercy. 51. So 13 over 51. Because here we drew a diamond first and then we went to get a heart. So there are still 13 hearts in the deck. And here we drew a heart first, so there are only 12 hearts in the deck. So Jess, you were right. So basically what we're going to do, you were thinking about this in the exact right way. What we're going to do is we're going to piece these together. So this is our first chunk. We're going to say our heart to heart path is going to be 1 over 4 times 12 over 51. And so that's going to be 12 over 204. And then we're going to consider this diamond to heart path, which is going to be diamond to, so a red card to a heart, 1 over 4 times 13 over 51. So that's equal to 13 over 204. And what we do is we add these together. Because just like on page 427, there are 2 different paths reaching to the same goal. We did this on problem 21 when we were looking at like going from A to C and then from B to C. We just add them together to get the final probability. And so the book is in fact right because it is 12 plus 13 over 204 is equal to 25 over 204. What a chore of a problem. Okay. But that is how you do it. I'm sorry for the delay in getting that done. No problem. You did most of the work. You really did. You were so close. Okay. Jess, would you like to talk about 8.2? We are about done time-wise, but I am more than happy to talk about independent events. If you'd like me to. Oh, cool. Okay. If anyone else has any questions about independent events, feel free to email me. Again, it's important to be able to recognize that events are independent. So that's going to be coming up in a lot of later problems. I hope I helped you guys with problem 34 on the homework and problem 35. We worked through it. Thank you so much to Jess for doing most of that problem for me. Yeah, so thank you everyone and have a good evening.